Little change of plan. We are going to start talking about fibers today. I decided to switch the last topics or the last parts because what I want to do, I want you to understand how fibers work. And then we are going to apply these fibers techniques to the final topic, which would be performant fibers. So we are going to create a specific mesh with the right topology, and we are going to use, let's say, structural performance in order to guide the fibers as they grow. Okay, so today we are going to concentrate on the fibers and on the importance of some decisions that we can take during the creation of these fiber systems. Okay. The technique is not, let's say, that complex. Fibers are basically a system that grows according to a guide structure. So basically, in order to create this fiber system, we are going to create a system of guides where the fiber can grow and move along these guides. So there are probably 2 or 3 important parameters that we are going to define in order to play with fibers, and mostly geometrical parameters, as you will see. We are going to start with simple system, 2-dimensional systems, in order to understand how tweaking some parameters affects the final result. Both, well, actually, only from an aesthetical point of view. Okay, so we are going to create a static fiber system at first, and then we will concentrate on structural behavior. So this part here, this let's say static fiber system creation is based on a Grasshopper plugin, which is this one, which is called Shortest Walk. Okay, could you please double check that you have this Shortest Walk plugin installed in your curve toolbar? If you go into the curve toolbar, in a utility section, you should have Shortest Walk available. If you don't have it, the Shortest Walk is available on Food for Rhino. It's a very simple plugin. We are going to understand how it works. Okay, Zagar, you don't. So let me double check here that we have Food for Rhino. It's worth spending a few time to install it because it's important. Okay, Adish, let's have a look here. Shortest walk, search, and here it is. Okay, it's this one. So you just go in Food for Rhino, and I guess you know how to install this kind of plugins. You see, it's a very old plugin, 2011. Okay. There is also another version, Shortest Walk Grasshopper. Actually, I didn't know about this. It's basically the same. It's older because it still works with Grasshopper with 4 and 5, so imaging. So I do recommend that you install the red one. Okay. So take a few minutes to install this. Download the well, actually there's been only one release, which is this one. It also runs in Rhino 6. As you can see, I use it normally. Yeah, I think that, sorry, let me double check here. Oh no, I think it's the green one because I see that it is for Grasshopper. This is strange because, yeah, I think it should install this one because else the red one is for Rhino, and this works with Grasshopper. So yeah, you should install this Grasshopper 090014 from December 3, 2012. So it's the green shortest walk Grasshopper. Yeah. Actually, the icon is red, so I suppose this is just for differentiating between Rhino and Grasshopper plugin. And as we are here, you can already understand what this component does in terms of behavior, or how it functions. And you see that there is a square grid, and this plugin, what it does, follows the grid lines from point A to point B. You can define point A and point B, and it follows the grid lines going from point A to point B. So the aesthetics, or the aspect of these flow lines, depends on the grid that you are using. Okay, Saga, thank you for being so fast. So you see that changing the grid actually changes the shape of the resulting path, and also changing the position of point A, point B has the same effect. So you have a different graphic result according to the grid that you are using and according to the points that you are using. Of course, we are going to see that normally the result that we are going to get is extremely simple. So we will have to understand how to add complexity to this kind of graphic result. Okay. So you see, even with the Voronoi pattern, which is basically random chaotic pattern, if you don't create the start point and end point in the proper way, you only get this kind of wobbling path, which is not that interesting, right? Maybe this one is a little more interesting because there is some kind of maze, and then you cannot go straight across the square lines. So we are going to deal with this kind of things right now. So remember that when you install this, it's in curve utility shortest walk. Okay. Actually, I'm going to grab it and place it here because sooner or later we are going to use it. Okay. So let's see how it works. Let's see what we can do with this. The easiest thing that we can do actually is use standard Grasshopper grids. So you know that if you go into the vector toolbar, you have the grid section here with a bunch of grids, from hexagonal grids to triangular grids. Of course, we're not going to use populate for now. Later, yes, we were going to use them, but let's focus on grids. Let's try to understand this behavior, especially the way this component works, and then we are going to get some complex structures. So let's start with a simple one, like the square grid. Remember that the square grid generates cells, and these cells, you see that they are 5 cells per row, per column actually, because I think, if I'm not wrong, these cells are oriented by columns. So the first 5 that belongs to branch 000 are this column of cells, if I remember correctly. Anyway, this is not the important thing. If you grab a panel and go and see what you have here inside, you have rectangles. Okay. We cannot use these cells actually for a very simple reason. If those are rectangles, it means that if we consider them like this cell here, and then there is the neighbor, which is here, I am creating here a gap, which is not, of course, it's not present here. They are perfectly touching and overlapping with the next cell. So if I have this, what happens is that if you consider the lines that are on the outside, they are just one single line. But every internal line that you see here, there are 2 edges, 1 and 2, and 1 here and 2 here, 1 here and 2 here. So we basically have double the amount of lines in this kind of grid. So first of all, let's get rid of those duplicated lines. Fortunately, well, it's very simple actually. We can explode these rectangles, So we get to the segments. We can also flatten this in order to understand that we have 100 lines, which is evident. It's too much for this amount of lines, also visually. And then we can rely on, for example, well, actually, I am sure that you have Kangaroo installed because it comes with Grasshopper and Rhino 6. But actually, besides Kangaroo, there are other plugins that contain the same command. So if I use a remove duplicate lines, you see that I have these two here that belongs to Kangaroo 099 and Kangaroo 2. It's a utility that is present in both versions. There is this one also, like that, if I'm not wrong, it belongs to Caramba 3D or something like that, you know. So, and there are also others, okay? But anyway, let's use the remove duplicate lines from Caramba, from Kangaroo, which I'm sure you have it. And so we pass all this list of line here, 100, and we get only 60. Now, this is the grid that we can use for creating our system. And of course, we can also parameterize the extent X and extent Y. So let's grab an 11 slider, plug it, one in the extent X and one in the extent Y. So we have a wider grid that we can change as we please, okay? And here we have changed the number of lines, of course, 2016, and in the end we have 1053. Now, normally, and this is something that we're going to see today, normally, in order to have interesting fiber system, we must work with a huge amount of data, okay? Because the complexity comes from also from the amount of geometry that we are considering, okay? So for now, we are only limiting the fiber creation to this grid, but later on we will see that things can become heavily stressful for the computer. But anyway, so this is basically the grid of lines that we want, the underlying grid of lines that we want to consider. And these objects here, they are the curves. Okay, so in the shortest walk, the first thing that he wants to know is what is the curve system along which you want to move from point A to point B. Okay, and then it asks for the wanted path. And wanted path, you see the hexagonal icon, which defines the data type, so the parameter, it's lines. You cannot work with curves, for example, or with point A, point B. So remember these images here, where you see point A and point B, which are the starting point and end point. They are not defined by via the point parameter. You need a line parameter. So imagine that there is a line here. This is the wanted path. So what I'm going to do right now is create a line parameter or line container, as you want to call it. Set one line and click from one point to another point, like this. And then this is going to be the wanted path. And now you see that if I turn off the grid, you see that this is the shortest walk between one point and the other. Of course, remember that this grid extends up to 21 and up to 24. Okay, so more or less here and here. So I can also change the line and obtain a different shortest walk. This is the base of everything. Okay, now let's try to tweak things a little, because this is not properly correct. It is not fundamental, as you can see, because even if I pick a random line, like this one, for example, starting from the center of one grid square to the center of another grid square, I still get this shortest walk. But actually, I don't know from which point or which end point of the grid lines I am starting. Because if I pick a point here, my eye tells me that it could be this start point or this start point, but there is some precise rule in order to understand where the fibers are going to be created from and what point they are going to reach. Okay, so one thing that we can do is this one. We can define the line, of course, and we can calculate the endpoints of this line. So we know what is point A and point B for us, okay? And once we know these 2 points here, we can find what are the closest points starting from these starting from these 2 points here along this cloud of points. Now, remember that in the square grid, this is important, the points that you see here lie at grid corners. So if I grab a point parameter and plug the points here, I'm getting the vertices of the cells, which also means that we have duplicated vertices. Well, not only duplicated vertices, because if you consider this point here, there are 4 vertices here. But in this case, it's not like with the cells, because the amount of points is already, let's say, optimized. Okay? So they are not just the vertices of each cell. They are exactly 1 point per corner. Okay, so we don't have to remove duplicate points in this case. So this becomes easy to see if we grab a 5 by 5 grid, and we should have 6 by 6 points, so 36 points, and you can see that it's actually what's happening. Okay, so in this case, because of the way that the square grid works, the points are only at the corners of the cells and they are not duplicated. So we can just grab these points in output, plug it into the cloud for the closest point, and flatten this thing. Oh, no, sorry, I picked the wrong closest point because I have many plugins here. So the points that I want to evaluate are these 2, and the cloud is going to be this one, and I need to flatten this cloud because it is actually not a list but a tree of points. So I'm going to flatten this. And you see that each point, the start point has its own closest point and the end point has its own closest point. So let's go back to our 21 by 20 something grid. So you can see that actually this closest point is giving us the closest point to the start and the closest point to the end point of our line. And what I want to do, I want to use these 2 points as the starting point and end point of my line. Okay, this helps to get more understandable fibers. Okay, at the time of creating the fiber system. Okay, so the closest points here are grouped because we provided a list of points and we are getting a list of closest points. Now, in order to create a connection line between these 2, remember that wanted path asks for lines and not the start point and end point. We can simply grab a polyline. So these 2 points are going to be used as vertices, and we get one single straight segment. So this is the original line, and this is the actual path for the fiber system, like this. And we get finally the result. So we can always define the line like this, but the actual line is going to use the closest points on the grid that we are using, on the underlying grid. And of course, we can change the grid and we can see what happens. Okay, so this is very basic stuff. We are just trying to understand how to prepare the system in order for this shortest walk to work properly. Okay, so we can switch. For example, I would skip the rectangular because it's basically identical. We can switch to hexagonal. Actually, we can also use the same sliders, but no, I prefer to keep these things separated because each grid works in a different way. Okay, we are going to see it right now. So you see that here we have cells, which are the hexagon, always grouped by column. But there is one particularity here, which is the points. The points are not at grid corners, they are at grid centers. So these are the centers of the hexagons. They are useless for our purposes. And so everything here depends on the cells. If I flatten this, I see that these are polyline curves, the hexagons. And so I need to repeat these explode and remove duplicate lines in order to get rid of duplicate edges in this grid. And so we have these 3024 lines, and in the end we only work with half the amount of edges. Okay, but this time we also need to derive the points in a different way because we have the cells here. So I'm going to use well, when you have a polyline, especially if it is closed and you want to extract the vertices, I do recommend that you use the discontinuity command, okay, and not just explode. Let's see the difference. If I calculate the discontinuity, I will have 6 vertices per hexagon, as you can see. You see there is 0, 0, n equals 6. So 6 vertices per hexagon. But if I explode this and take a look at the vertices, I get 7 vertices per hexagon, because this is a closed polyline. So the last vertex is coincident with the first one because the curve is closed, it's an hexagon. So when you have closed curve and you want to extract the vertices, just one instance for each vertex, you must use discontinuity. So I'm going to use discontinuity. Remember that we are extracting the vertices per each hexagon. And now, yes, we have duplicated points here. Because if you think about this hexagon here, this vertex is shared with this other hexagon and this other hexagon. So we have 3 points, 3 coincident points per each one of these points at the interior part of the grid. And so once again, we use kangaroo, remove duplicate points. Remember that discontinuity explodes or extracts the vertices per hexagon. So we have a data tree, we flatten this, and we plug it into remove duplicate points. So we are decreasing from 3,000 to 1,000, more or less. So this is going to be the grid of points from which we are going to calculate the closest point. Okay, and this is going to be the line system for the grid. And as for the rest, it's absolutely identical. We can also copy paste all this block here. And so my point cloud for the closest point is going to be the unique points from the remove duplicate points. And I'm going to grab another shortest walk. The curves is going to be the hexagons. And the wanted path is going to be this polyline here. Okay. So now if I turn off the first part of this definition, I now have the hexagonal, well, the hexagonal path, let's call it so, from point A to point B, closest to the actual line that we draw. So this is the actual result. We can also get rid of the construction things, and we only see the final path for this shortest walk. Now, of course, this is something that I'm not going to use also the triangular grid. You already got the behavior, but you have to prepare things differently according to the result that you get from this automatic grid creation. Later, we are going to work with custom grids in order to see how this affects the fibers aesthetics, especially. It's going to be more interesting than this. But let's also see another problem that we might have here. What happens if I want to use, for example, multiple lines, like one starting from here to here and the other one starting from here to here? Hit enter, and you see that things simply stop working. Now, why they are stopping working? Because when you evaluate the closest point, in this case, we are using the endpoints for each line. Okay, so I'm going to visually see them here in Rhino preview. So we are calculating the closest point. These are 4 points in just one list. So actually the polyline is not giving us one line, it's giving us this Z-shaped line. So this is a curve. This is a curve, it's not a line segment. So wanted path is actually receiving a curve, it converts it into a null object because it doesn't understand what is getting in, and the shortest wall stop working. So we must eventually recreate the correct structure in order to have 2 separate segments. And this can be done by tweaking things here. For example, if I graph this, What I'm telling right now is that I want two separate lines, basically not just one list. So when I calculate the endpoints, I will have start point and end point for the first line and start point and end point for the last line. So you see that there are two start point. One is for the first and one is for the last line. So when I calculate the closest point, I'm calculating the closest point for basically start and end point for the first line, which are these n equal 2, and then start and end point for the second line. And on the other hand, I have the whole cloud of vertices for this hexagonal grid. And so here we get closest start point and closest end point for the first line in the first branch. And in the second branch, we get the closest points for the start point and end point of the second line. And therefore, the polyline generates two segments. Okay? And they are passed the wanted path, which is receiving two lines, actually, which are these two separate segments, so it can work. And we get this. What we can do with this technique now. Let's see this grid for a moment. What I want to do, I want to place, for example, a circle. Well, actually, maybe let me see if I use a circle container and I set one circle, I can draw it right here. Yeah, okay. So I can draw a circle here. And what I want to do, I want to calculate the, well, actually, in order to calculate the center of this circle, I can do a couple of things. If you go into the curve and analysis, you will find the polygon center that it only works with polygon, but there is a plugin, if I don't remember, yeah, there is a plugin which allows to calculate the center. This plugin is Heteroptera. Okay. Oh, by the way, do you have Heteroptera installed already? I think this is one of the fundamental plugins that you should have installed no matter what. Yeah, Atish, perfect. And Sagar, do you have it installed?
No, I don't.
No, you don't? Okay, so Heteroptera is a very, very, very important plugin. Okay, I think that I don't know if you saw, but on my website there is a recommended list of plugins. It's a post in the blog section where you will find the, well, probably the ideal setup for Grasshopper according to the discipline that you are into, like, for example, architecture or interaction or media or design or whatever. Heteroptera is a super powerful plugin that allows to do many, many interesting things. This is actually a geometric utility. It's very stupid. It just returns the center of a geometry of a circle. But if you don't have it installed right now, I can. Okay, perfect. So now that you have it, you could also calculate the center of the circle, but it's not that relevant. You can also, you can also create a circle like the traditional way. So just creating a point, set one point, put it there, and keep this radius a parameter, like something like this. So for example, now if I take this circle and divide it with a divide curve, now we have a list of points. We can create lines from the very center to the points around this circle. And we can use these lines as paths, as wanted paths. So I simply plug them here, they get grafted, and finally I should get this kind of star-ish system of shortest walks. And of course, we can parameterize things here in the divide curve, for example. We have the count parameter that we can use for tweaking this. So we are getting complex patterns over an hexagonal grids, which are pretty interesting. Okay. So what we are saying right now is this: the aesthetic of these fibers. These are not still yet fibers; they are just shortest walk. We are going to understand how to tweak them in order to have this kind of organic aspect. But for now, the important parameters for us are, of course, the grid, which defines the shape of the underlying structure, and also the extension, of course. Then there are the lines that we are going to use, so the paths that we want to convert into shortest walk. Okay, so it's important to define not only the amount of grid, but only the configuration, the general configuration of grid. Now, in this case, we have radial lines, and so we get this kind of star-ish fiber system. Okay, so this is the first thing that we might want to consider. The other thing is what happens when we already have created the shortest walk. What we can do with this. Now, the shortest walk has several outputs, and we are interested into the shortest walk output, which are these polylines here. Okay, and these are polylines because they simply follow the grid lines that we are using as curves. Okay, so the first result that we get are always polylines. Okay, but if we want to convert this into organic shapes, what we could do is, for example, rebuild this thing. Now, if we rebuild this line, we are going to start getting different shapes. Now, you know that the rebuild command in Grasshopper, if you don't provide any degree to this input, it simply uses the actual degree from the input curve. So these are polylines, so degree is automatically going to be 1. But I want this curve to be organic. So I'm going to define a degree between, well, let's say 2, even if it is not properly organic, to 5. So I want this curve to be actually curved lines, okay? And another important parameter is the count. Count is set by default to 210. And as we are going to work with a degree that is ranging between 2 and 5, we can have a number of control points ranging between 3 and whatever. I'm going to spend 2 words on this in a moment, but 3 to whatever, I suggest we don't exceed 50 because it's going to be absolutely useless. So 3 to 50, I think it's a good starting point. Now, I think, I don't know actually, because I have no clue on this, but I think you understand how the NURBS curve topology works. Nevertheless, let me spend 2 words on this. The degree and the amount of control point are interconnected via the equation of the NURBS curve. And the relationship between these 2 values is very simple. When you want a curve to have a specific degree, you need at least this amount plus 1 control points. So that's why when this is degree 2, the count must be at least 3. If you decrease the count to 2, you can only have degree 1. Okay? So either you see this as the degree is equal to the amount of control point minus 1, or in order to have a defined degree, a specific degree, you must provide degree plus 1 control point. Else you will get a lower degree. Now, this is NURBS topology stuff, but we are not going to discuss this in detail, but this is why I define the range of this slider this way. Of course, when you have set the degree, you can use degree plus 1 control point or more, and you will have a curve with this degree. So if I switch this to 4, I still have degree 2 curves, okay? But if I keep this to 3, and if I keep 3 control points and increase this to 3, now in this case, the curve that we are getting right now is not going to have degree 3 because it lacks control points, okay? Especially if I go with 4 and 5, okay? So you need always to have more control points than the degree that you are defining. Okay, so that's the way you can tweak these sliders. Now, I don't want degree 2 curves because they are not organic shapes. They are basically segments of hyperbolic segments. Okay, so I prefer to have a single organic shape. So I increase the degree to 3 and start working with the number of control points set to 4. See that 4 to 3 doesn't change anything because we are not working with degree 3 in this case, because we have the same amount of between control points and degrees. So from 4 up, you will have some change in your curve. Okay. So what are we going to do with this? Well, let's start with let's say 50 control points. So degree 3 and 50 control points. Okay. And for now, let's just bake this result. So I'm going to bake this group of curves, so I have them available in Rhino. Okay, and you see that with this amount of point, 15, which is not, let's say, a huge amount of control point, but it's already something. You already are preserving the hexagonal aspect of these lines. Okay, let's decrease this to 40, and let's bake this again, always grouping the result. And let's decrease this to 30. And let's bake this once again by grouping the lines. Of course, let's decrease this to 20 and let's bake them. And 10. Well, actually, when the lower you go, the smoother the curves become. So from 20 to eventually 15 instead of jumping with a 10 step. Okay, so what we are getting here is this kind of lines with a more or less organic shape according to the amount of control points that we get. You see? So we are getting to this kind of organic irregular behavior, more or less with an hexagonal pattern, underlying hexagonal pattern, but as we decrease the amount of control point, we obtain lines that tend to escape the hexagonal rule. This is another principle that we are going to use when creating the final fiber system. Okay. So before creating the paths or the shortest walk, the important things are the grid and the desired path and their configuration, their distribution. And after creating the shortest walk, what we are interested into is tweaking the shape of the final path. We are going to work with this later on again. Now, as you already installed Heteroptera, thank you for doing that so quickly. As you already did it, let's see what other things we can do with this. Especially, we are going to concentrate a little on the original grid right now. So, for example, in the vector grid group of comments, there is also the populate, right? So what I can do, for example, right now is populate to an area. You know that this can also be a region with whatever shape. In case you want to do this, you must use the populate geometry, but we are going to stick with the rectangle right now. So the only thing that I need actually is a rectangle with some parameters here in order to define the width and the height. Okay, so we have this variable region that we can use like the input for the rectangle, the region for the populate, sorry, and we have the amount of points that can be set to 101 because it is actually 100, so we want to also be able to increase this the amount of points, you know, something like this. Now, this is a random set of points inside one region. And remember that the shortest walk works with a curved system and a wanted path. So if we want to use the shortest walk right now, we cannot rely on this population of points. We need to create interconnections. Okay. Now, the easiest way of creating interconnection between a point cloud is going to the mesh toolbar, triangulation, and work with Delaunay edges, which is something that On one hand, it's extremely simple. On the other hand, it's absolutely, let's say, poor as result. Okay, because you only get this kind of triangulation here, extremely automatic triangulation. Remember that between the two outputs, the important thing are the edges, not the connectivity. The connectivity is the connectivity scheme. So it basically tells you which points are being connected. These are the indices of the points that are connected with these edges. But the edges are the actual lines. So if we use these as the curves for our shortest walk, I'm not going to repeat now the closest point thing. I just want to see what happens in terms of path. If I create a single line and set one line from here to here and plug it here, I get these kind of things. Due to the fact that we are working with a random population of points, the triangulation always comes irregular. So it's the Delaunay edges are themselves, let's say, chaotic or random. Okay, so this is something that guarantees the fact that the path is no longer regular as with the grids that we were using. Now, as you can see, the Delaunay edge is basically a uniform or well a continuous network of edges. Okay, so if you decide, for example, that you want to start your line from one point and you want to reach to the other point, there is always a more or less continuous path that leads from this point to the other point. Okay, so you always get this kind of almost straight connection. But the interesting thing is what happens when you have a non-continuous network of lines, because in that case, you would force the shortest walk to find a different path between the start point and the end point. So in this case, if you want to work with Delaunay edges, what you can do, for example, is this. You could, for example, random reduce these edges. They are 6, 8, 9. So if I say I want a reduction from 0 to 6, 8, 9, I then have the whole set of lines if I set this to 0. But if I start reducing this, I am eliminating some edges from this. And if I use this narrow list of lines, then the shortest walk cannot walk straight from one point to the other. It must find another way of connecting these points. So you see that, for example, well, it reached a point where there is no connection, so it fails actually. But you see that in this case, it is forced to do all this path here to get from point A to point B. Okay, and as the populate to D depends on a seed, but also the random reduce depends on a seed, you have additional control over this design because you can set a seed, for example, like 1 million for the seed, and eventually you have no straight connection or no continuous connection. But if you change these, sooner or later you come up with other results, as you can see. We are shuffling the population of points, which changes the Delaunay edge connections. Okay, but you can also do the same with the random reduce. So we can also change, once we have the population of points, which stays static, what we are shuffling here is the connection scheme. Okay, and so we can come up with different paths according to the random population and the random shuffling of the connection lines. So this makes this process a little more interesting because we are not using regular grid, and we are also forcing the shortest walk to take different roads according to the connections that we are creating. Okay, so randomness is way more interesting when you work with fiber system. It's not always like that. I mean, there are also other ways of working with regular grids that allow creating interesting fiber systems. For example, let's leave this aside for a moment. I'm going to create another script, a little script, very simple. And this time, yes, I'm going to use, for example, the rectangular grid. And I'm going to define the size of this rectangle with a 5 slider. 500 slider, of course I want some rectangles, so I'm going to also define the extent X and extent Y. So I want this kind of grid here. Okay. You know, we have cells. So what I want to do, I want to deform this grid. So it is a regular grid, and it's a good basis point, a good starting point for our process. But I don't want to work with this regular grid because I already know what type of behavior is going to come up from this thing. So what if I distort this, deform this regular grid? So for example, I don't know, something stupid, okay? Some basic manipulation. If you have, and if you know the paneling tools plugin, this is something that you can achieve easily, okay? If you don't have paneling tools installed, you can create some simple, let's say, point manipulation, like moving the points accordingly. So these points here, you see they are 45 per column. Okay, so you see that we have 20 extent X and 44 extent Y. So you see that we have 45 points aligned vertically. Okay, so if I flip this matrix of points, now I have 21 points in 45 rows. Okay, and if I want to move these points in the Y direction, because I want to move them vertically in this top view, like this, I can use, for example, a graph mapper. This is very basic techniques. I'm pretty sure you already know this kind of processes. I want to use, for example, some Gaussian curve, and I need a range of values between 0 and 1. How many values do I need? 1 per each point that I want to move vertically. So is this amount of points is 21. Okay, so I can simply take this data tree here, calculate the list length of each branch. I have one number. I'm only interested in one list item because I need just one value between them. Sorry, flatten this. I get 21, 21, 21 because the branches always contain the same amount of points. And so I know that I need 21 values. So if I plug this here, I get 22 values right now, but I need only 21. So steps must be x minus 1. And so I have 21 values between 0 and 1, and I have this graph mapper that is outputting the corresponding value along this curve here. So if I do this, I can move the points according to this curve, and you see that they only raise up in the center area. And so we can change where this deformation happens. We can increase how high these points go. With this curve, we can flatten the curve a little, so we distribute the displacement along the whole line of points, and so on. Okay. We can also change the graph type. For example, if we want a periodic displacement like this, we can create this kind of situation. And now we have this kind of thing here. How do we get back to the grid? If you don't have paneling tools and you don't want to use paneling tools, you can always flatten this set of points, and eventually you can use them for creating a surface and a mesh. Okay, and you can extract the vertices. So it's very simple to use this kind of process here. On the other hand, if you have paneling tools, which is worth giving a quick look at it, you see that there is this grid actually. You can use the same points that you have from here directly. So you can create grid just by defining the amount of rows and columns. So points is as list. So we are going to flatten this, and we are going to define the amount of row and column, which is basically this amount here, but these are columns and rows. Okay. So if I want to have this And this, let me turn off all this stuff here. Let's see here, we have a null object because remember that when you create a rectangular grid with 20 extent x, okay, so 20 columns basically, you are creating actually 21 columns of points. Okay, so now the grid is actually interested in the vertices and not in the cells. The rectangular grid is interested in defining the amount of cells horizontally, but this is asking for how many points you have in the rows. And so we must define, for example, that. Oh, sorry, I think I also switched this. Yeah, so we should have. No, it was correct. We should have this value +1 and this value +1 in order for this to work. So x +1 and also x +1. Let's see. It's still null. Let me see if I am doing things properly. Nope. List of points. Row indices. Sorry. No. There is another way of creating the grid. Sorry. Yes. I must use the. I must create directly the grid. It's easier because if not, I'm going to have to provide the indices. It's quite boring creating series of numbers and so on. But anyway, we can define a planar grid directly by defining the distance and number of columns and rows that we want. So in this case, for example, it's better to use the same parameters in order to create exactly the same grid. In this case, the only consideration is that in this case, in the rectangular grid, the only thing that matters is the size of the cells and the extent in the two directions. While here, apart from the base point, which is actually the same as the rectangular grid, you need to define the direction, which by default are x 100 and y 010. So it's identical to the rectangular grid. In case you want a distorted grid, something like let's say something like rows or columns with inclination, you can change these two vectors here. And this is the distance between rows, which is actually the size in our rectangular grid. So we can use these two sliders. And this is the I number, j number, which is the amount of points in the two directions. Okay. So it's easier to create the grid in paneling tools using exactly the same parameters that we have here. Just remember, you have an additional setting, which are the orientation of the horizontal and vertical axis. And once we have this, we can use grid attractors. It's very easy to work with grids when you use paneling tools. For example, let's say we want a curve attractor, okay, something like that. The grid is going to be this one, and the curve attractors as least can be more than one. So it's very easy. If I create a curve, something like this, and reference this in Grasshopper, set one curve, this one, plug it here, and you see that the grid is already being deformed, okay, according to the presence of this attractor. And that is magnitude, which by default is set to 1, but you can set this to any value, let's say 0 to 10. So 0 is nothing. When you increase this, you see that the grid is actually being distorted. So it's very nice to work with paneling tools because once you have this grid, you can simply, it's called cellulate. So you can cellulate this grid or generate borders if you want, which is very easy. Or you can cellulate it and you get this kind of connection schemes. And of course, what we are interested into here are the wires. So the wires, if you take a look at the icon, they are already lines. It's a tree, it's a data tree of lines, but we are only interested in a list. So we get this. And it's very nice to work with deformed regular grid as a basis, but deformed regular grid because you have this kind of guided behavior. So you can start with a regular grid and deform it accordingly to your needs. It's very nice. And the deformation can come from whatever consideration. For example, architecturally speaking, this could be a patio, for example, with some path where where people can walk, and then you have all the design surrounding this path, concentrating on it. So it depends on what's the design that you are going to create with this geometry. What's the meaning of this geometry? Okay, I'm going to leave this like internalized data, so we are not dependent from Rhino as for this curve. So you can also play with these alternatives in order of creating complex grids starting from simple ones. So paneling tools is very useful in this case because it allows to reduce the effort for creating variations on this grid. So this is somehow a controlled deformed grid. What can we, going back to randomness? Okay, so going back to our delineators that we were using right now, right in this situation. Delineators work with whatever set of points you provide. The important thing is that it must be a planar set of points. Okay, so they don't work in 3 dimensions. What we can do, for example, always staying in 2 dimensions in order to create an extremely complex connection scheme. Let's go back to our random population of points. Okay, so something like this. So I'm going to copy paste this rectangle with this populated 2D with this amount of points and this seed. I'm going to copy paste it right now. Also, I would also invert these 2 blocks because this is already randomness and this is still an in-between randomness and regular grids. So regular distorted grid and randomness. And now let's talk about randomness, but serious randomness. Okay, so let's start with this population of points. You might know that Grasshopper randomness is actually a pseudo randomness. So this set of points is actually not a random set of points. I don't know if I'm sure you know this, but just so that you get the point, if I take a random component and you do the same, and you just plug a panel here, you will get exactly the same value, 0.771094. Now, this means that this component here works exactly the same in my computer here and in your computer over there at your local time, whatever. In different conditions, you always get the same result, which means that this is not a random value or a real number, random value. Randomness in Grasshopper depends on this parameter here, which is called seed. So this is the seed of random engine. So everything depends on it. If you have the same range and the same amount of random numbers, so range and number has the same input, and we have the same seed, then we have the same value. If we change the seed, we will get a different value. Of course, we must work with different seeds in order to obtain different values. Okay? So every time you see a seed, there is some pseudo randomness going on. And also the populated 2D is based on the seed. So this set of points is not precisely random. Everything depends on the seed. Now, if we want to work with actual random populations, so my population of 237 points inside this 29 by 37 rectangle be different from yours, then we must change the seed accordingly. There is a way of doing this, of course. You could, for example, bind the seed value to time, for example, or I don't know, to the local weather, to local temperature, you know. So like detect what's the environment conditions and translate them into a, I don't know, multiplication factor for this seed. So each one of us would have a different seed automatically, okay? But this is another chunk of script that you might need to implement, which is somehow it's not, let's say, convenient to do that. Or you can use Heteroptera. Now, Heteroptera is a totally different way of handling randomness. And if you go into the uncertainty, the group of comments, you will directly find that there is one thing which is called seed generator. Okay. Now, let's plug a seed generator. Let's put it on inside the canvas. And just in order to double check this, take a panel and plug this here. And you will see that this number that I am getting here is different from yours. Also, if I take this component here and copy paste it like this, and plug it into this panel together with the first one by clicking Shift and Wire, you see that this is actually generating a different number. And if I copy paste this and plug it another time, I get another different number from the previous two. So if you want to work with randomness, I do recommend that you work with Heteroptera because it's the best way of creating random behavior in Grasshopper until today. I don't know what would happen tomorrow. Okay. So in this case, for example, if we want a population of points which is different from computer to computer, actually, we just use a seed generator, and this is going to produce a different value for each one of us. How does this thing work? I just make assumptions here because I don't know the developer, but I think that this seed generator is actually defining an integer number as any seed, basically. But it's doing this by binding this value to local computer time, probably. And so you have an algorithm inside the seed generator that, according to the time the component is placed inside the canvas, it generates a different value. And I think that this is, let's say, bound to time because once you have this seed generator placed in your canvas, if you go here in solution recompute or you hit F5, the seed generator emits a different value. So it's evidently bound to the local time in your computer. You can double check this by plugging a cable here and hitting F5. You see that each time that I hit F5, it generates another random seed. So it depends on time, probably something else, I don't know, but the important thing is that you get a different result. And in order to have exactly the same value, the same random value, we should hit F5. We should place this component at the very same moment in the canvas, and then hit F5 at the very same moment in order to have the same variation. So it's extremely unlikely that we have this kind of thing. Therefore, this is actually a random situation that we are getting. Okay. We are going to use Heteroptera not only for creating this random population of points, but also for creating the grid, the actual grid. And Heteroptera is very good in doing this. There is another group of comments here, which is called networks. Okay, so if you take a look at this, you see that there are several comments here. Some of them are extremely complex because they are based on the connection scheme that you want to create between these points inside the cloud. So the whole first part, construct hyperindex, intertopology, network editor, and point enumerator topology graph display, it's extremely complex. You should define the connection scheme by using the indices of points. It's somehow very boring. Okay, but there are some automatic components, like for example this incestuous network. Now, incestuous network is quite funny as a name, but the meaning is that it creates a network inside one unique list of points. And we have one unique list of points here, so 237 points in one unique group. So if I take incestuous network here, this can work with this list. Don't plug this yet, okay? Don't do that. First, before plugging the list of points, let's define these two parameters here. So these two parameters ask how many connections do you want to be starting from each point of this cloud, okay? And up to what distance you want this connection to be created. So this is very important because if we set these parameters here to the default, so you see that distance is optional and number is optional, okay? So if I plug this population of points to here, each point will be able to create all the connections that connect this point to all the other remaining points at whatever distance they are, okay? So first of all, let's limit the amount of connection. Let's grab a 5 slider, for example. Okay, so now each point can connect to up to 5 surrounding points. Let's leave distance for now, because this is more than enough to limit the amount of connection, and let's connect the points. And so you see that we start getting some Delaunay style connection scheme, but you see that this is not a uniform network of triangles. You see? So according to the amount of connection that I want to create, if I decrease this, I start getting this kind of random connections, because we have actually a random connection, a collection of points. To connection, no matter the distance. Okay. If I also limit the distance, for example, see this bold square measures 5 by 5. So if I grab a 5.00 slider, I am forcing the connection to reach up to 5 units from the point that is being taken into account. So at this point, even if I increase this, connection happen locally. You see that if I don't use this, there are also large connections happening along this point cloud. But with this, I can limit the distance for this connection and create this kind of random connection scheme or random pattern of lines. So this is very interesting, because I can use this set of lines as curves for our underlying grid for the fibers. Okay, and so create random paths also. Everything will depend on this C generator. Remember that if you hit F5, you change absolutely everything. See? One thing that might happen in this case is that by reducing the distance and the amount of connection, you might get extremely disconnected networks. So in this case, for example, if I try to use a path that starts from this point and I wanted to get to this point, there is no way for the shortest walk to find the solution, because there is a physical disconnection of this element from the rest of the grid. Okay, so this is the only risk that we have in this moment. But we can also do other things. So for example, let's say that I want to guide these fibers. You see that we are concentrating on the grid right now. So let's say that I want to guide these fibers using the underlying grid. Before creating the incestuous network, which is a good way of creating random connections, let me turn the preview off and let me move this away. What I could do, for example, is now that I have this and I want to create a specific, let's say, area in which the fibers are going to grow, what I can do, I can also create something like a closed region, something like this beam here, import it inside Grasshopper, so set one curve, and I'm going to internalize this directly, so we no longer need it in Rhino. And I'm going to use the point in curve command. So I'm going to evaluate if these points lie inside of this region. Okay. Now this is going to give us a relationship which is 0 outside, 1 coincident, and 2 inside. I'm looking for the 2 inside. Okay, because I'm only interested in the points that lie inside this region. Okay, so I'm looking for 2. So if I take equal to, this is going to emit a true-false series of Boolean values. And once I have this, I can call pattern the whole set of points that I have here according to this pattern. And you see that I only have the inner point inside this region. And these are the points that I want to use for the incestuous network. And so I start to obtain this kind of connection inside this beam, actually. And if I increase the distance, you see that now I follow this. See? So I can create a fiber system in a localized or a contained area. Okay? The important thing is to keep the network as continuous as possible in order to create the proper continuous network. Okay? Once we have this, for example, we can go back to our shortest walk, use this network, which are basically a list of lines as curves. They don't have duplicated lines in this case. They are simply one line per connection. And you see that if I use this line, I already have this kind of shortest walk. Of course, if I set one line starting from this end to this end of the beam, I get a completely different path. And I can hit F5 as many times as I want, and I get each time a different path. And as this seed generator is extremely variable, you see that it works with a huge amount of numbers, or very big numbers. It's very unlikely that every time you hit the F5, you get one of the results that you already obtained. So probably, or I'm almost sure, that each time you hit F5, you get a different path. Okay. The limitation in this case could be the connection scheme, but if you change the point cloud, you will also change the connection scheme. So everything is extremely random in this case. So you see that each time I hit F5, I get a different point cloud. We could also do a quick visual test with a limited amount of repetitions, of course, or instances. If I use a data record, no, not this one. If I use a data recorder, I can store the different point clouds each time I hit F5. And we should see that this point cloud increases and increases and fills the space each time that I hit F5. So you see that we never get a point cloud which is identical to the previous one. See, there is always a slight variation. So the path is always going to be different. Okay. So these guys here start to be quite interesting, but they are not enough. Actually, we are still far from having the desired result. We could also do something like this with this shortest walk. For example, well, we could also do some, let's say, implement another random solution for creating these wanted paths, because we have this cloud of points inside this beam, actually. So what we could do, for example, could be to create random connection lines and use them as wanted paths. Okay. Remember that the only condition is that these lines must be. Remember that we were using a where is it? Where did I place this? A graph when we use this closest point technique. But in the end, we must provide a list of separated lines. Okay. So the important thing is that if you want to use more lines, you must have, of course, separated lines when they get inside the wanted path. In order to do this, we could also do something like this, like random reduce this list of points. We can calculate the list length of this point cloud, so we know how many points we have, 82. And say we are only interested in having 2 points left. So if I make a subtraction, I can define the amount of points that I want to leave with this random reduce. So reduction would be 80, and we will only have 2 points, according to one seed. Okay. But if I grab another instance of this random seed and place it here, you see that now I get a different couple of points. And if I hit F5, each time I get a different pair of points. Okay. What happens if I use 2 random seeds here? Now I am getting 2 separate lists of points. So if I grab a polyline and I connect this, I get 2 different paths. Okay. How many paths do we want? Well, it depends, because I can create more and more and more and more. Okay. And the problem is that in this case we are getting polylines and not straight lines, because I am working with 7 points per branch. Okay, so we cannot do this. But if I flip this matrix, I am confident that you have some data manipulation skills, so you know exactly what I'm doing right now. We finally get 7 polylines. So one line, sorry, 7 lines. one line for each couple of points that we have here. So according to how many paths we want, we can increase this from 1 to whatever value we need. And so if I take these polylines, which are actually lines, and plug them into here, I start getting several organic paths or several the shortest walks along this shape. So things are starting to be quite interesting. Also remember that another parameter that we have is the amount of points. So if I increase this, I have a more dense point cloud inside this beam, actually. And I also have the random seed generator, like for the cloud and for the random reduce. So if I hit F5, I always get a different shorted walk system inside this area. Okay. Remember that we are only discussing this from the aesthetic point of view. So there is actually no functional or structural meaning in this. It's just to obtain some kind of fiber systems. But you see that the potentials start to be very high in the moment we start to work with randomness and therefore with heteroptera. Let's leave this aside and let's also consider the three-dimensional scenario, okay? Because the three-dimensional scenario is going to become very important also when we are going to discuss the structural behavior or performance of these fibers, okay? Now, in order to create a network of connection in 3 dimensions, there are 2 things that we can do. One is very easy, because now that we are working with heteroptera, we can simply take, for example, a populate 3D, define, for example, a domain box as a region. It's a box, actually, and define the width, depth, and height of this box with a 11 slider, for example. So we can have this volume variable in the 3 dimensions. Okay? So something like this. And this is a 3-dimensional set of points, but this is still one single list of points. Okay. Also, we can 101 this count, and we can already use a seed generator in order to define the shuffling of this point cloud. So F5, F5, we can change the point cloud and the amount of points. Okay. You see that I tend to increase the amount of points because I told you that when you work with this technique with fibers and shortest walk, the more geometry you have, the more interesting the result. Okay. So what I'm going to do right now, I'm going to use the same, exactly the same ancestors network. Before plugging the points, remember to set at least the number. So let's grab a 5 once again. And also let's grab a 5.00 again for the distance. And now we can plug the points. So you see that now we have a 3-dimensional connection system inside this volume. Okay, and everything depends on how many connections we want to create and up to what distance we want to have this connection. If the network is continuous enough, we can use the same method for creating the shortest walk. So we can create a shortest walk component. This network is going to be the curves. And now what I'm going to do, I'm going to change things a little, just defining a line by its endpoint. And so I'm taking a point here and another point here. So this is going to be the wanted path. And I'm going to set one point on one end and set one point on the other end. So I have this line. Actually, this is, oh yeah, the points are isolated. This is what can happen when you have a non-continuous network of points. But anyway, we can still change things. I can still take these points here and move them around and see if at some point, by getting them closer to each other, we have a continuous network eventually. I'm not sure. And yeah, here in this case, they must be very close because eventually this network is extremely discontinuous. But in this case, for example, if I have this kind of large distance and this reduced amount of connection, maybe if I just increase the amount of points, I could already come up with some solution. You see that for a moment there was a very complex line, but anyway, when I have, this one, for example, you see that it's extremely disconnected because of the reduced amount of connection that I am creating. But if I increase this, I have very short walks. Okay. And we can hit F5 and have eventually different solution. We can also start now double checking. You see that each time we move this, eventually we will find some solution. It depends on how dense the network is and how these points are close to a closed loop or a non-isolated starting point. You see? Now, if we work with randomness in 3-dimensional, things start to be a little more complex because of this problem. You should have a network, an incestuous network, continuous enough to guarantee that each couple of points you will have a defined path. Okay, so it starts to be somehow tricky to always find a solution. But there is another alternative to this one. So I'm going to leave this, which is the calculation of the shortest walk, which we are going to use also with this second possibility that I'm going to implement right now. This is based on the incestuous network, so I'm going to group this and leave it here aside, just to have a couple of solutions in this case. And the other one that we are going to see is by using the Voronoi 3D component. And don't get scared about creating Voronoi 3D with this amount of points. So creating 650 three-dimensional cells is going to be like stressful for the computer. But if you don't work with this amount of geometry, you will get very dumb connections. Okay. At first, I'm going to decrease this to a lower value, like something like 250 or 300. The container, the box, is going to be this one, and the points are going to be these. So let's wait a few seconds, and here is the 3D Voronoi diagram inside this volume. Okay. Now, in this case, if I use all the edges of this diagram, I will always find a closest, a shortest walk between the ends of the endpoints of this line. So what I'm interested into right now is deconstructing these B-reps, or if you want, you can grab the B-rep wireframe. They always give you the same result. So here we have 7,470 edges. Here we have 7,470 edges. Okay, it's absolutely the same. It depends on what you want to do. Normally with this fiber theory, I prefer to work with deconstruct B-rep because we also get the vertices. And remember that, and we will use it later, remember that we are interested in working with the closest points normally in order to define exactly what's the starting point, the end point of the shortest walk in over the grid that we are using, and not starting from a random point in space like in this case. Okay. But anyway, let's concentrate on the edges for now. This is a data tree. We will have duplicated edges every time we have adjacent faces for these cells. So we must get rid of these duplicated edges. Well, more than duplicated edges, because probably there are more than 2 copies of them. So I'm going to use once again the remove duplicate lines by flattening the input, because this is a data tree. So we have 7470, and here we have 2719. Okay, so a little different. And now if I go here and plug these lines, I will always have the shortest walk, because this is a continuous network of connections. And so if I start moving this point around, you see that I always find a solution. Okay, there is no gap between one solution and another. What can we do with this? Let's start playing around with this algorithm. Okay, so now that we are in 3-dimensional, let's see what we can do with this in a 3-dimensional structure. So instead of using a dummy line like this one, which is an extremely variable and random line. I don't want to use this. I want to use a different approach right now. So creating something meaningful. So for example, let's calculate the volume of this domain box. So we have the centroid. And what I want to do, I want to deconstruct this point. Okay, something like this. And I want to construct a new point using only the x and y coordinates. So I need the center of the base of this cube. And the next step is going to use the height of the domain box in order to define the the center of the upper face. Okay. So what I'm going to do, I'm going to use another construct point already connected to the xy coordinates, but the z is going to be the actual z for the height of my box. So starting from the centroid, I derived the lower center and upper center for this thing. And now I'm going to connect. Well, I'm going to connect the base with the top, but I don't want to connect this with directly with this line because it's quite stupid, right? So the only thing that I get if I do this is another path, more or less vertical, that flows along the Voronoi edges. So I don't want this. What I want to create some kind of tree-like structure. So I want this to be the base of the tree, and I want branches happening here. Okay. So how can we do this? Well, always using Heteroptera, we have access to a very interesting component. So I'm going to leave this line here for now. But remember, this is the base point. This is the upper point. Okay. So if we go in uncertainty once again, there is one command which is called point emitter. And if I plug the emitter, if I plug the upper point as emitter, now I have a cloud of point being generated around this point. Now remember that almost everything you grab from Heteroptera plugin depends on time. You see that seed is optional, right? But if I hit F5, you see that here we are changing the cloud of points. We are also changing the cloud of the Voronoi 3D. That's why it's so slow, because our Populate 3D is based on this random. Every time I hit F5, it shuffles this point, and this is recalculating 241 cells. That's why the definition is slow. Okay, but the important thing is that it also updates the point emitter, because we see changing this little cloud of points. Radius defines how far from the emitter these points are being created. It has a value between 2 and 10 in this moment. Okay, but if I plug here a slider 11, it means now from 0 to 11 as the domain, and I can increase this and move these points far away from the emitter. Okay, and it's a three-dimensional point cloud, so you see that this point can go 27 in any direction around the point in 360 degrees, so also up. But the important thing is that we have a planar distribution of points. So we can right-click on three-dimensional on the icon and pick planar. So now these points can only be generated at a maximum of 27 units around this emitter point, but horizontally, like if there was a circle here. And all these points are inside this circle. How many points do we want? Number. So number is set to 24. They are too much right now, so let's say that we want just 5 as a starting value. You see that each time you change this, you change the whole cloud of points. You see, you never get the same cloud of points. This is because this is always based on time. Or according to my opinion, it is based on time. So what I'm interested now is in connecting the base point with each of these points here. So creating this system of lines. They all start from the same point, but they reach different points at the higher height, well, at the top of this box. And so basically what I'm getting are these kind of random paths or shortest walk inside this box. Of course, we can shuffle many things here. If I hit F5, everything changes, both because we are changing the point cloud for the Voronoi diagram, but also the population of the point emitter. Okay, so if I want more branches, I can simply increase this thing here. So it becomes very nice to have this kind of branching system. Now, the problem is that this branching occurs starting from the lower point. So all the paths converge inside in this point here, and then they split and separate as they grow vertically. Okay, but it would be nice, for example, to have this branching occurring at a certain height. Okay, so in this case, for example, we could simply I don't know, start the branching, for example, from the volume, from the centroid, okay, and then just connect all, all the lower part with one single path, one single line. So we will have one random or Voronoi style uh, lower part for these paths, and then the paths will split and irradiate from this center volume point. But this is something that you can easily achieve with some tweaking in this line input. Okay. And one parameter here, which is very, very important, is of course the resolution or the density of this Voronoi diagram. So you see that with 241 cells, we get this kind of, let's say, bulky and large segments. But if I increase this to 500, don't be afraid of using this. Just give it time to calculate things. It might be stressful for the computer, but sooner or later you will have the solution. You see that you have this kind of more, let's say, interesting, they look something like lightnings or something like that, rays or something like that. But it's very nice to work with this kind of things. And also remember that we still can rebuild things later. Okay, so if you don't like this faceted or segmented aspect, you can always rebuild this with a run or organic degree and just define the amount of control points accordingly. Yes, this is very cool, Atish. And this is just the beginning, because we are going to implement this further in order to have a more interesting behavior. But you see that now we have this kind of organic lines. Of course, where the moment you have overlaying lines, they will not be coincident, because the paths have different lengths according to the edges that they are covering, the Voronoi edges that they are covering or using as the guide. And so the distribution of control point will be different, and therefore you will have this kind of wobbling lines, not coincident with the others. This is something that's very interesting, because we, in the end, will have to give some thickness to this object in order to make them three-dimensional. Okay. Like a little art installation inside the virtual box. Yes, you might see it like this. Actually, remember that in this case, for example, we are working with a very simple system. It should be nice, for example, to create some, let's say, branching system like this. I don't know, starting from each corner of the box and tending to the center. So see how, for example, like some energy connecting the vertices to the center, something like that. Yeah, very, very artistic interpretation. I agree, but we will use it also for functional and structural purposes. So you will see that it also has different meanings. But yes, for now, we are more concentrated in the static value. So I agree with you. It's more like an artistic thing. So let's have another approach to this, because we need to have complexity here. So what I'm going to do right now, I'm going to go back to a two-dimensional scenario, because I want to introduce another mechanism for creating this branching system. And what I want to do, let's work in 2D. So I switch to the top viewport, and I'm going back to create a rectangle with an 11 slider in order to have, and I want this to be a square, so I don't need to have a couple of sliders. and I want to populate this region with 101 points inside, and with a random seed generator. Okay, so we have full control over the randomness of this population of points, and also on the amount of points. So F5, 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 we already know that. What I want to do, I want to create a network of connections. Okay, and let's start with a very simple one. I'm not going to use the delineages. I'm going to use right now a Voronoi pattern. Okay, so I'm going to use this population of points and this rectangle as boundary. Okay, and this is the underlying grid for our fiber system. Of course, I want to have a very dense pattern in order to have some interesting variation on the path of our fibers, and also we must get rid of duplicated lines, okay, because they are polyline cells, and so we must we can use the explode, and we can use the remove duplicate lines in order to get rid of the duplicated segments. So 3669, 1882, okay. And I also want to work with the closest point right now. So I need also to use the vertices. Remember that vertices is not the proper approach, because in the end you have duplicated vertices for each closed polyline. But in this case, we are going to use the point cloud. So we are going to get rid of duplicated points. So we also need to remove duplicated points by flattening this input and plugging the vertices. Okay, so we have basically, here we had 4,300 more or less, and here we have 1,251. Okay, so we no longer have duplicated points. Now, as we saw when working with the shortest walk, these are going to be the curves. So we already have this set properly. Now let's concentrate on this point, because what I want to do is something different. Until now, we have worked with straight lines as the path, right? And so it's very easy to, for example, understand that if I grab a line that goes from here to here, what the shortest walk will do is run through this connection scheme and find the shortest walk. It's very simple to understand this, right? It's very obvious. But what happens if I want to draw a curve like this? Like this extremely variable NURBS curve, very organic, right? Now, the wanted path only understands the lines, okay? So even if I have this complex path here, the obvious things that I could do could be to draw a line from start point to end point, feed it inside the wanted path, but then I will get one straight or straight-ish path between these 2 points, not taking into account this shape of this path. So we must find a way to force the shortest walk to use this kind of shape here. Remember that the shortest walk only understands lines. Okay, so we must come up with a strategy in order to define this kind of forcing this shortest walk to use or to consider this kind of shape. Okay, so this is the next challenge that we have. And we want to use also the closest point techniques in order to have all these lines anchored to the actual grid of points that we have here. So the endpoints of the connection lines. So how do we do this? Let's see. First of all, let's consider some kind of complex curve in order to have some meaningful result. So what I'm going to use right now is going to use some maths to create a curve. So I will use some expressions. let me rename this thing. You see that I have variable x and variable y. This is because my Grasshopper is set to use full names. You might only see x, y, and so on. I do this because when I give class to the university, I need the students to clearly see what's the name of all the things. But anyway, let's rename this to simply A and X. Okay. And so what I'm going to use right now is I want to create some kind of a spiral, okay, a spiral curve. So I'm going to use an equation for determining the x coordinate of the points, and another one for determining the y coordinate of each point of this curve. And the equation is going to be a multiplied by x multiplied by, well, it's irrelevant, like sine of x. Okay, something like this. And on the other hand, I will have another one which is identical, but it will use cosine. And so in order to have this producing results, we need to provide a. A can be any number, actually. Let's grab a slider between 0 and 10, and let's see what happens. I'm improvising, right? So I don't know what's going to happen. I'm only quite sure about the equations here, and I need x. Now x is at the same time this multiplication factor here, and also the argument for these trigonometrical functions. And so it's an angle, basically. And Grasshopper measures angles in degrees, in radians, sorry. So what I need to do here is use a Radiance Converter, like this one, and define the angle between, I don't know, 0 and, well, let's do something like 0 to 10, okay? But what I want to do, I want to place here an expression that multiplies the value by 180, okay? So when this is 0, it is basically 0 degree, but when this is 1, you have 180. So half circle, 1 complete turn, 1 turn and a half, and so on. Okay, so this is the meaning. And I want initially to start with 100 degrees, so it means 3.14, which is pi. And I'm providing this to the x and to the x here. And so we have some coordinates. Of course, we have 0 because this multiplier is set to 0, but if we increase this, you start to have some coordinates. And now I don't want to provide one single x. I need this to be a multiplier and x to be a variable. So even if I use this as the upper value or the upper angle that I want to obtain, what I need to do is to create a, well, we can create a range, and we can define the resolution of this curve later. So you see that now we have this kind of series of values. I'm going to provide them, to plug them into the x of each expression, and so I get a series of coordinates. And if I construct a point like this, we should start seeing a spiral. Yeah, here it is. And this sets the size, basically, while this sets the number of turns that we are going to do. And these steps defines the resolution of this spiral. So if I set this to 101, in order to have a huge amount of points, I start to get a very continuous set of points, which is useful when we want to create a smooth curve. Okay, and with this we define how big it is. Okay, so we are creating this kind of thing, and it also means that I want this plane to be symmetrical with respect to the origin. So I want this spiral to be inside this square. And in order to do this, what I can do is basically do another thing. Take this this spiral curve. Well, actually, this is not yet a curve. I can use an interpolate curve in order to connect all these points and get this extremely complex line. Okay, and then I can calculate the bounding box for this object. And once I have these, I can calculate the area. Remember that this is a flat box, so I can treat it like a rectangle. And I'm going to scale this geometry according to this center with a scale factor which is something like bigger than 1. So we will have, basically I'm doing this because I want the rectangle to be wider than the actual curve. So everything in our script will be now based, instead of this rectangle here, will be based on this scaled geometry here. This is a flat box, so if you try to plug it inside the region and inside the boundary, you see that everything works perfectly, because this is not actually a bounding box. And this rectangle can go away. So we can decide the gap between the curve and the rectangle by tweaking this scale factor here. Remember that when you increase the size of this rectangle, you are getting also bigger cells in the Voronoi diagram. Okay. So the lines are here and the points are here. Now, what we want to do is use this curve as the path or the general path for our system. The problem is that the shortest walk only accepts straight line segments, not even polyline. Okay? So we must come up with a strategy to do this. And the strategy is going to create several paths, several straight paths along this main path here. There is one obvious approach which we are going to analyze right now before having our break, which is very simple, extremely simple, I would say. So once we have the original curve, which is this one, we just, I don't know, something like divide it with a specific amount of segments, of points, sorry, which is going to be a variable amount of segments. We can then use a polyline to convert, basically. We could also rebuild the line, but actually it's more or less the same. And once we have this polyline, we simply explode it into its segments. And here we have independent lines, 42 paths that we can use in order to create this thing. So this is the obvious approach. It's very, let's say, straightforward. We are converting the organic curve into a polyline, explode it, use the line segments in order to feed the wanted path in the shortest walk. But it's very limited approach because the fibers in this case are just, well, a segmented polyline following the Voronoi cells. We want to increase the amount of complexity here in order to create some more interesting pattern inside this rectangle.